Today we're going to be starting our unit on trigonometry, and some of this is going to be a review of things that we did last year, but trig forms the basis for a lot of things that we're going to be doing later in this course, like complex numbers and vectors, and so it's important that we have a really strong basis to work with here. So before we get started, let's go and take a deep breath, and then let's begin. So first I'm going to ask you to recall that trigonometric functions, all six of them, sine, cosine, and tangent, which we studied last year, and secant, cosecant, and cotangent, which you may or may not be familiar with, they're all periodic. And periodic functions are families that basically repeat themselves after some certain period length. And this means that trigonometric functions very commonly have multiple solutions, sometimes even on infinitely many. And we need to come up with methods and understanding that allows us to find all of these solutions. What I have down here below is I have the graph of y equals sine x. And so I want you to sort of think for a moment. If I asked you to solve the equation sine x equals 0.8, right, you would effectively be asked to find out where does sine have a height of 0.8. And so you could even sort of imagine like a line being drawn here at a height of about 0.8. And you can sort of see a lot of the solutions here, right? And what it means to be periodic is it means that when we notice that this right here is a solution, if the period length of sine is 2 pi, then when we find one solution here, we're going to find another one 2 pi later. And we'll find another one 2 pi later. We'll even find another one backward 2 pi back this direction. And all of these blue points are all related to one another, right? But we also need to remember from last year that in addition to those infinitely many solutions that you can find by adding or subtracting the period length, some trig functions, notably sine, cosine, cosecant, and secant, will have two different categories of infinitely many solutions. So you'll notice that I found this one, and I could find more of them by adding 2 pi to that one, but adding 2 pi to that sort of neglected some of these other solutions. Like you'll notice that there's another one right here, and that one is also repeated 2 pi later over here. And it's also repeated back this way, 2 pi backward. So with sine, cosine, secant, and cosecant, we're going to have sort of two categories of infinitely many solutions. And again, we need to get into how do we find those things and what methods do we use to make sure that we don't miss some of these infinitely many solutions. So before we get into examples, and today's really just going to be a lot about examples, I wanted to review for you the method that we use for solving simple trigonometric equations. And I want to remind you that what I mean by simple trigonometric equations is we only ever try and solve a trig equation when we have reduced it down to a trig function equals a number. Trig function equals a number. Trig function equals a number. So if you had, for instance, something like 5 sine x minus 1 equals 2, you would work with this thing so that sine x had been isolated. You'd have 5 sine x equals 3, and then you divide the 5 over sine x equals 3/5. And at this point, you would apply this method that we're about to talk about in terms of how we go about solving these simple trigonometric equations. So step one is either mentally or by the calculator, and by mentally I mean like unit circle values. So either mentally or by the calculator, you're going to find the principal value of the angle solution. So you're sort of going to find the first real solution to this thing. Second, for sine and cosine, you're going to remember that there is always a secondary value of that angular solution. If you're working with a sine equation, you find the second one by taking your first solution and doing pi minus that. And if you're working with cosine, you take your first solution and you do the opposite of that, so the negative of that solution. If you're working with a tangent style equation, nothing to worry about. There actually is no secondary solution like sine and cosine have. Okay, so first step, find the principal solution. Second step, find the secondary solution by using one of these two relationships, depending on whether it's sine or cosine. After you have found those two solutions, your primary and your secondary, then you'll go through and add or subtract the period of the function as many times as you need to find all the solutions that are needed. Okay? Remember that the period for sine and cosine are 2 pi, and the period of tangent is pi. Okay? So this is sort of the method that we have to solve trigonometric equations. We find the principal value, we find the secondary value, and then and only then we start adding and subtracting the period to find all of the different solutions. So we're going to go ahead and go through one example here that's a non-calculator example, and then after that, all the rest of them are going to be calculator problems. So this question says, find all solutions to the equation sine x equals a half on the interval from negative 2 pi to 4 pi without using a calculator. Okay, so as we mentioned, the first step that we're going to take is to find the primary solution. So to do that, we effectively just need to say that x is the inverse sine, or the arc sine, of 1/2. And for that, we think to ourselves, where on the unit circle do we find a sine, a y value of a half? So if you're sort of thinking about your unit circle, a y value of a half would be there. This is sort of the 30-degree angle. This would be x equals pi over 6. So we found our primary solution. Okay? Now we move on to our second step, which is to find the secondary solution. And we remember that in the case of sine, we find this by subtracting from pi. So if this was our first solution, we can find our second solution by doing pi minus that thing, which gets me 5 pi over 6. Okay. Now the third step is that we're supposed to add and subtract the period length, which is 2 pi, as many times as we need to find all the solutions on our interval. So I notice that pi over 6 definitely fits onto the interval. It looks like I could find another solution by doing pi over 6 minus 2 pi. That would be pi over 6 minus 12 pi over 6, which would get me negative 11 pi over 6. Looks like I could also find another one by doing pi over 6 plus 2 pi, which is plus 12 pi over 6. That would get me 13 pi over 6. I might be wondering about whether I could do pi over 6 plus like another 2 pi, so I guess 13 pi over 6 plus another 12 pi over 6, but that gets me 25 pi over 6, which is larger than 4 pi, so I didn't need that one. So this is another solution for us, this is another solution. And we find all of the other ones. Oops, I just realized I labeled this thing x2. This should have been 3 and 4, because x2, we had already sort of given that name to 5 pi over 6. So 5 pi over 6 is a solution for us. So it looks like we can find a fifth solution by subtracting 2 pi. I'm going to do 12 pi over 6 just to sort of save some time here. This would be negative 7 pi over 6. So that gets me another solution. And then I could do one more by doing that 5 pi over 6 plus 12 pi over 6. Adding those together gets me 17 pi over 6. And at this point, I've got these 6 solutions. I recognize that if I added 2 pi again to this, I would go past this. And if I subtracted 2 pi from this, I would go beyond my left boundary. This is the process that we use for solving all trigonometric equations. So now I've got another example here that I'm going to have you try on your own. You do get to use a calculator for this one, and before you start on it, I would remind you, you can do these problems in degrees or in radians. You do that on your calculator by going to mode and then switching between radian and degree. And the important thing is to look at this interval. If they are asking for answers on an interval from negative 2 pi to positive 2 pi, those are radian values. So make sure that your calculator is in radian mode before you start this problem. All right, so now that you've tried this one on your own, let's go and go through it together. We're going to do step 1, where we find the primary solution. For this, I just did on my calculator the inverse cosine of negative 0.73 and found that that was 2.39. So I'm going to call that x1. Step 2, we're going to go on and find our secondary solution. Oops, just realized I forgot an equal sign here. For the secondary solution, we're going to take our primary solution, and in the case of cosine, all we have to do is make it negative. So the opposite of that is negative 2.39. Okay, so now I have a primary solution and I have a secondary solution, and we check our interval really quickly. Turns out both of these answers are on that interval. So we've just found 2 solutions to our problem. And the third step is I now need to add and subtract the period length to see how many other solutions I can find that are on this interval. Okay, so working from the primary solution here, I could get a third solution. Well, let's see here. This number is already positive. If I take a positive number and add the period length of cosine, if I add 2 pi to this, I'm already going to overshoot 2 pi. So my only hope for finding another one here is to take my answer from previously and subtract 2 pi from it. When I do that, I'm going to wind up with, let's see here, this minus 2 pi. This is going to get me negative 3.89, which again we notice is on our interval, so that one works. Okay. I'll then find my other solution for this one, x4, by doing negative 2.39. And similar to the reasoning we used before, I don't want to subtract 2 pi from this, because if this number is already negative, subtracting 2 pi is definitely going to put me smaller than negative 2 pi. So my only hope here is to add 2 pi onto this. And when I add 2 pi onto that, I wind up getting positive 3.89. And there they are. I found my 4 solutions. The reason I didn't do anything more than this is I, again, recognized that if I added 2 pi to this, I'd go above 2 pi, so I'm clearly not going to get another one here. And similarly, if I subtracted 2 pi, I would go, well past negative 2 pi, and so that's why I knew there weren't going to be further solutions. All right, so here we've got just one more example for you to do before we move on and talk about reciprocal trig functions. So find all solutions to the equation 5 tangent x minus 4 equals 7 on the interval from 0 to 3 pi. So go ahead and pause the video and make sure that you can get through this one on your own. So hopefully you remember what we said earlier, that we really only solve trigonometric equations by first isolating the trigonometric function. So you'll want to add the 4 over and divide by 5 first. So you should have wound up here with tangent x equals 11/5. Your next step is to do the inverse tangent of 11/5. And when we do that, we find that our x value here is 1.14. Okay, we check and make sure, yep, 1.4 is on this interval, so we found our first solution. Now, in the last 2 problems, we went and did a step 2 where we had to find our secondary solution. But remember, tangent doesn't have secondary solutions. Sine and cosine do, tangent doesn't. The reason for that, by the way, just really quickly to review with you, the shape of tangent looks roughly like this. And so when we draw a line through it, you'll notice that the line only ever hits each tangent curve once. Whereas with sine and cosine, if you take one period length of sine, that sine graph gets hit twice. So the reason that sine and cosine have sort of a primary and a secondary is sort of the shape of the graph and the fact that each period length gives 2 solutions. Whereas with tangent, each period length only gives 1 solution. So that's why we're not doing that part. So the next step here really is for me to just find further solutions by adding and subtracting the period length. Remember that the period length for tangent is pi. So if I did 1.14 and subtracted pi, I would go below my lower bound, so I don't need to subtract it. I'll just do 1.14 plus pi. And when I do that, the solution that I get is 4.29. I could find another one by doing that 1.14 plus 2 pi. And when I do that, I get 7.43. And I mean, I suppose that I could find another one by doing 1.14 plus 3 pi, but I can tell that that's going to take me beyond my upper bound, so I'm done. I found the 3 solutions, and there they are. Some students find solving trigonometric equations to be a really, really scary process, but I think if we follow this sort of 3-step process of finding the primary solution, if necessary, finding the secondary solution, and then adding and subtracting the period length, it really doesn't end up being a very scary process. Now, the rest of this lesson is going to be devoted to talking about the reciprocal trigonometric functions. Basically, I assume that all of you are familiar with sine, cosine, and tangent, and you may or may not have heard of cosecant, secant, and cotangent. If you haven't heard of them, this is going to be your brief introduction. Okay? These are called the reciprocal trigonometric functions because literally all they are is the reciprocals of the basic trigonometric functions. So the cosecant function is simply the reciprocal of sine. The secant function is simply the reciprocal of cosine. And the cotangent function is just the reciprocal of tangent, which means we can think of it as cosine over sine instead of sine over cosine. The way that you can remember how these match to one another is that each pairing only has one co in it. So it's cosecant that pairs with sine, secant that pairs with cosecant, and cotangent that pairs with tangent. Okay, so before I get into solving equations with these things, I just want us to practice evaluating them, right? So if somebody asks you what is the secant of pi over 4, all this means is what is 1 over the cosine of pi over 4. So then we think about our unit circle for a moment, and we recognize that the cosine of pi over 4 is just the square root of 2 over 2. So I just need to do the reciprocal of root 2 over 2, which is 2 over root 2. If I wanted to, I could multiply top and bottom both by the square root of 2 and get 2 root 2 over 2, which means this is the square root of 2. Okay? So the secant of pi over 4 is the square root of 2. So pause the video for a moment, see if you can work through the cosecant of negative pi over 3 and the cotangent of 5 pi over 6. So the cosecant of negative pi over 3 should just be 1 over the sine of negative pi over 3. Okay. So again, here we think about our unit circle. We go, negative pi over 3, that's down there. So this looks like it's going to be 1 over negative root 3 over 2. So then I'm just reciprocating that. This is negative 2 over root 3. And again, if I wanted to rationalize that, I could make that negative 2 root 3 over 3. And that's what the cosecant of pi over 3 is. For this last one, the cotangent of 5 pi over 6, we just think about this as being, we can either think about this as being 1 over the tangent of 5 pi over 6, or we can go straight to sort of the reciprocal of what we usually think of. We could think of this as just cosine 5 pi over 6 over the sine of 5 pi over 6. And then again, we're thinking about our unit circle. The cosine of 5 pi over 6 is negative root 3 over 2. The sine is positive a half. These 2's cancel out, and this winds up being negative root 3. So hopefully you can see that evaluating these reciprocal trig functions is really just as simple as figuring out what their reciprocals are and then reciprocating them. It's a fairly straightforward thing. Now in the last couple of examples, I want to show you that we can even solve trigonometric equations that involve these reciprocal trig functions. Now, really important note, your calculator more than likely does not have inverse secant, inverse cosecant, and inverse cotangent buttons. So the secret to solving these problems is to just convert them back to their non-reciprocal forms before you actually solve them. So in this problem, we're going to start by isolating the cosecant. I'll move the 13 and I'll move the 6. So I'm going to have cosecant x is negative 13 over 6. Okay? So there it is. Like that's what this thing is. Now, I want to solve this thing, but I can't inverse cosecant because my calculator doesn't have that. So what I'm going to do is I'm going to recognize, hey, wait a minute. Cosecant is just the reciprocal of sine. So this means 1 over sine x equals negative 13 over 6. Great, so now all I have to do is say, all right, let's reciprocate both sides. Sine x is negative 6/13, and now this problem is exactly the same as everything else we have done so far in the notes today. We're now going to go through our 3-step process. Step 1, find the principal solution. Step 2, find the secondary solution. Step 3, add or subtract the period as many times as we need to find all the solutions. So if you feel comfortable with that, go ahead and do that on your own right now. If you'd like to see me do it, we can go through this one, and there will be one more for you to try on your own after that. All right, so when I did inverse sine of negative 6/13, I found that my first solution, my primary solution, was negative 0.480. So I've got one solution here. Now when I go to find my secondary solution I find by doing pi minus that first solution. So when I did that, I got it to be 3.62. Okay? Now, checking my interval, I wanted the answers between 0 and 2 pi. So this one worked. This answer was between 0 and 2 pi. This one, however, was not, right? So now I go on and I say, well, okay, there could be another solution that I get by doing that one plus the period length of sine. Remember, that was step 3. When we punch that into our calculator, we find that this other solution is 5.80. So these are the two solutions that I found that were on that interval. And if I think for a moment, I can recognize if I add 2 pi to this again, I'm going to go above this. If I add 2 pi to this, I'm going to go above it. And if I subtract 2 pi from this, I'm going to wind up too small in the interval. So these are all of the solutions that we find for this problem on this interval. Here we have one last example where you can try this on your own. So the first step here is going to be moving these things around. I'm seeing this to be 3 secant x equals 4. Looks like that's actually negative 4. and that means that secant x is negative 4/3. We remember that secant x is 1 over cosine x, and then we can reciprocate to find that cosine has to be negative 3/4. Okay, so at that point we're set up and ready to solve this thing. We do x is the inverse cosine of negative 3/4, and then we can throw that at our calculator to find that our primary solution is 2.42. Checking really quickly, that is on the interval, so I'm going to go ahead and box this one. Okay. Then we jump sideways and do step 2 where we find our secondary solution. Our secondary solution is, remember with cosine it's really straightforward. It's just the opposite of that primary solution that you found. That one is also on the interval that we're working with. So we've completed step 1, finding the primary solution. We've completed step 2, finding the secondary solution. The third step is where we add and subtract the period length, 2 pi, to this as many times as we need to find all of the other solutions. So it looks like I could find a solution here by doing 2.42 minus 2 pi, because I can, let's see, I think that one's going to fit. So if we do this minus 2 pi, I got this to be negative 3.86. Oh, nope, that's more than 3. That's sort of smaller than negative 3.14, so we can't get that one. We could potentially find one, though, by doing 2.42 plus 2 pi. If I do that one, I wind up with 8.70. And we check really quickly, 3 pi, that's 3 times 3.1. Yeah, that's 9 point something. So this one's definitely going to work. Okay, we've got this solution that worked. Subtracting 2 pi is definitely going to be too small. It looks like maybe we could find another one by doing negative 2.42 plus 2 pi. So here for this one, we find that x4 would be 3.86. I got myself confused there. 3.86, which gives us another solution there. If we added another 2 pi to that one, we're going to go beyond this because this is already above pi. So at this point, we found our 4 solutions. These are all of the solutions to the equation, and we're done solving it. So moral to the story here is even when we have these reciprocal trig functions, we can apply the exact same sort of 3-step method or process to solving these trigonometric equations. So best of luck as you try the assignment on your own, and please remember to send me any questions if you've got them.